So, kinematics again. The first time we talked about it was on differentiation. And that's because motion problems from what you have seen in physics sometimes are best explained in calculus. Especially when you do not have, how do I put this? You don't have like regular cases. So it's not like, oh, somebody is going this way, then you can easily get this stuff. But the moment it's becoming like a function, the displacement is represented by some function in terms of t, then it's not something you have to then start plotting graph and do all those kind of stuff. So calculus comes in handy here. And we have seen initially during our application of differentiation lessons, some of the applications, some of the ways you can find, maybe velocity for example, all you have to do is differentiate the displacement function, is that not? And especially for the instantaneous velocity, remember instantaneous velocity is that tangent at that particular point. If you remember what we discussed then, if we have, this is my displacement, you can see what I call the displacement time graph. It means we are plotting displacement against time. It's different from the one over there, velocity time graph. Okay, so very different, all right? So for displacement time graph, if there is a tangent here, the gradient of this tangent is the gradient of this curve at this point, right? And that gives you the instantaneous velocity of that object represented by this graph, whose motion is represented by this graph. We talked about that in the calculus, in the differentiation. So it's just the same thing. We're just like repeating some of them and then reversing it because now we are in integration, which is anti-differentiation. That's the difference. Okay? That's why I just compress the whole thing together. So quickly, displacement of an object is position relative to the origin. Displaced. I'm here now. And Krista pushed me. I've just been displaced to this point. This is my displacement, this gap, relative to the origin. Okay? And of course, after a particular time, the velocity of an object is the rate of change of displacement. Okay? At what rate was I displayed? Which means the gap with respect to the time it took me to get displayed. So Krista could push me and I go slowly to that point. But then Krista pushed Karen and she jumped fast. Our rate of displacement is different, even though we have been both displayed. Okay? She displays us maybe by 5 units length or distance, but then it took me maybe 5 seconds to move. I'm so stubborn. So my rate is different, but Karen is so obedient. Okay, I go. 1 second, she's gone. She's very fast because she loves food, by the way. Anyways, so that's that. Then here, just like we did in differentiation, I like how the book organized it, so that's why I use that format. They talk about average velocity before the instantaneous velocity, just like we did in differentiation, remember. Average velocity, and then the average rate of change, then instantaneous rate of change. Remember that? So, same way, average velocity will be the final velocity minus the initial velocity. The change in velocity, because the change in velocity will be the final displacement minus the initial displacement, then divided by change in time. Just like we did in differentiation. And this is the instantaneous that we've talked about. So because in this case now, you are dealing with the function, the gradient of that function at a particular time. You are not considering this minus this for the average. Am I making sense, please? All right. So that's that about that. Then from here, from the instantaneous one, you can always get the velocity function back. The displacement function back from this one, just by integrating both sides here. If this is as a result of the derivative of this, then this will be as a result of the integral of that. Okay? So don't forget that. So quickly, now changing displacement. We've talked about changing displacement over there. Maybe this should have even come first. But anyways, the change in displacement of an object, as the name implies, what is the change of that displacement? So the origin is that door, but I was pushed from here to this place. my change in displacement is not everything. It's just between here and here. But remember, we always talk about displacement with respect to the origin. This is the origin. But this is where I was when I was displayed. To get this, you have to consider, okay, what is the gap from here to here? Then what is the gap from here to here? Then you can now subtract the two to get my change in displacement. Because I wasn't here at that point. Okay? So, our change in displacement is simply the S2, and we know that S of anything is with respect to the origin. Okay? Anyways, and with this, you could see clearly that it is same as this definite integral. Because if you integrate your VT according to this, you get some S function. You get ST function, right? And if you substitute, so you integrate this, you get ST, then you have this substitution T1, T2. Does that not? And by the time you substitute the upper minus lower, this is what you get back. So when somebody talks about the change in displacement, it's actually this definite integral within that time. Okay? So basically, what it's saying is that you don't have to first get your function S, substitute T2, substitute T1 and subtract, just find the definite integral. And you already know definite integral. So we don't need to waste so much time on that. And the next thing is total distance travel. Now, the distance travel, now this is a velocity time graph. Okay? The distance travel is given by this. See, it makes sense even from here. When I was pushed, isn't this my distance traveled? Right? Which is what we already talked about as a change in displacement. So we have just copied and pasted what we said before. But I didn't put absolute value here and I put absolute value here. Can somebody tell me why? What? I could have negative, depends on the direction now. If I was here and I push back, or I was here and I push forward, I could have, you know, now my direction comes in. Your velocity is not speed. So you are not just dealing with the magnitude, you're dealing with direction. I can have it either way. But if I'm talking about my distance, displacement and distance, that's different between them. One is a scalar quantity, one is a vector quantity. For my distance, I just have to have a scalar value, no direction. So that is why this will not be a negative. So this is also one of the reasons you can quickly link it to area under the curve. Can we see that? So the total distance traveled within this time is actually the area under this curve. And that you can also use in some of your physics stuff. They give you, most of the physics problem will be like a linear motion anyway, like you see straight line, and they tell you find the total distance traveled in the journey. All you have to do is find the area of the triangle, the trapezium you can see in your velocity time graph. And you can see that from here. This is a general function. It could be a line, it could be anything. It could be a parabola, it could be an hyperbola, we don't care. Okay? So that is why this has to be positive. Of course, maybe this could have been outside instead. We just want to retain the positive. Okay? We're not saying that that function has to be positive itself. Am I making sense now? So I think it's better we just put it outside. Or we put the minus if it comes out to be negative. Once you already know what your curve looks like, if you do know what it looks like, you can always determine how to manipulate it using your knowledge of definite integral. Is this going to be this plus this? Is it going to be a minus for one part? So that is why I'm linking it to the area bounded. So it is now left for you to figure it out based on your knowledge of area bounded by a curve. But along the t-axis, which is like our x-axis, then we're not using the y. Am I making sense? So the last part is acceleration. This is easy. Acceleration is just rate of change of your velocity, isn't it? Okay? So that's just the final velocity minus initial velocity, and blah, 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 like that. And then the change in time. And we already know this from differentiation. that when your acceleration is the derivative of velocity, and velocity is the derivative of this, so that's like second derivative. And similarly, you can now integrate. If you integrate this, you get, if you integrate this, you get this. If you integrate this, you get that. Now, this is where your particular value comes in. You remember particular value? You integrate to get the value of C. So for questions like this can be given if, for example, I have my acceleration function. I'm interested in some displacement function. It means when I first integrate my acceleration function, I will get velocity. I must have been given a particular value to get the C at this point. Then you integrate again to get your S. Okay? But if the question is about total distance within an interval, then you don't have to waste too much time. Once you get here, you just do your definite integral. You don't have to get the original function first. Am I making sense? And the last but not the least, speed. The speed is just that magnitude of the velocity. Okay? The speed is just the magnitude of the velocity. That's it. Oh, my velocity is minus 5 meters per second. Your speed is just 5 meters per second. So when your velocity is minus, it means you're slowing down, right? If it is plus, it also depends on your acceleration. Just like we have acceleration and deceleration. I believe you've done some of those in physics. Yes? Talk to me, physics student. Everybody's physics student, right? No. What are you doing? You're not doing physics? What?
With a passion.
Isn't that part of physics?
Yeah, exactly.
Because I'm wondering, wait, you're going to study math, you didn't do physics? Really? What's going on? Anyways. So, any questions here? Alright, so let's see, let's just take some random questions from the book and try. Then while you are solving something, I will... Okay, I can also, maybe we can play some of the example. Let's see, initial, these are easy stuff. I don't want us to waste too much time on easy stuff. This is average velocity, no need for that. Instantaneous are this, is derivative, you already know this from previous ones. Okay, let's look at... I hope everybody is going home with their book. Okay, how about you try this? Let's see which one is sweet. Number 5 or number... Do we need to play any of the example, or should I just go to the questions?
So we can just try a question first.
Speak louder, sir.
Just try a question first, see how it goes.
Okay. All right, let's pick this question 8. Try this question 8. The velocity of a moving object is given by that. If s is equal to 16 when t is equal to 0, find the displacement function. Explain why the change in displacement of the object and its total distance traveled in the interval can be both represented by definite integral that. I think that one is easy. Find the total distance. So you can skip B part, just go straight to C. Because that's what we have just talked about here. Understand? So just go to 8A and C. And please be fast with that. Talk less, focus more. Thank you. If your discussion is about the integral, why not? Please keep talking. If it's not, stop it. What?
What page is that?
62339. It's showing up. It likes to show up like that.
Just want to make sure everything's right.
Just get it. Quickly. That question 1A is what we've done under what topic or subtopic? 8A, I mean.
Functions.
Under what topic or subtopic? Particular value. Under particular value. You know what particular value means? Because when you integrate, you get a function, and that function does not contain C, so you don't know the intercept, and that's just family. It represents family of functions. So, but when you are given specific values, you can use that to determine your C, and you can restrict it to a particular function. That's why we call that kind of problem particular value. We'll still talk about the word particular in differential equation, particular solution. Quickly, please. I'm just going to pick some, maybe 3 to 4 random questions, because I want us to start differential equation today also. Lillian, you done? Yes? No? I believe everybody has their WeChat, so I can move to the next stuff. So I will put
So
some.
we know from here that with the displacement function, if we put in S0, we will get 60. That's what we do here. And then you see down there, ST equals integral dt dt. So I did integral, and then dt, and then you substitute the t for 0, because it's the same t, right? And it's the same. And then we integrate this. You get half a second. Sure. dt is velocity.
Are you done? Oh, with AC. Okay. Sorry. Try this question 1.
You're not supposed to play with it, you're playing it afterwards.
Not 8. It's 8 Z or 6 Yeah. 这样要可我有4分钟的时候，我有他的标准是。
关这个是。